we'll do that.
Mm-hmm.
Okay, so today we are very happy to have Dmitry Levkov joining us from Moscow. He is going to tell us about cold birth and bright death of Bose stars. Dima.
Okay, thank you. Thank you, Lem. And I think that I should thank everyone who will see this video in the future. So today we'll cover two topics, and the one was the old one, and the organizers insisted that I will tell about the kinetic formation of Bose stars by gravitation interacting light dark matter. And my second point will be a death actually of Bose stars by developing a parametric resonance into the photons. So the first topic, in the first part, I will consider just the dark matter inside structures. An example of the structure is the galaxy, for example, a dwarf galaxy, and we know all the kinematic parameters for this galaxy. And well, the properties of dark matter are more or less known, but the masses and some uncertainty. We don't know the mass. But mass should be larger than 10 to the minus 22 electron volts, just for the de Broglie wavelength to be smaller than the radius of the galaxy. And actually, if mass is smaller than 10 to the 2 electron volts, then the occupation numbers of these particles inside the galaxies are larger than 1. And this means that these particles are necessarily bosonic. So in the wide region between 10 to the minus 22 electron volt and 10 to the 2 electron volt, the dark matter is bosonic, and it is non-relativistic inside the galaxy. But actually, the last fact about this this region is that the Broglie wavelengths of these dark matter particles, mv to the minus 1, is larger than average distance between the particles. This means that the wave functions of these particles overlap, and if we let them interact anyway, they will try to thermalize and form Bose-Einstein condensate. So if they would be interacting, they would form a Bose-Einstein condensate. So I will consider this region of masses below 10 to the 2 electron volts and above 10 to the minus 22, which is fuzzy dark matter actually. And I will consider formation of Bose-Einstein condensate inside the structures, inside the galaxies or smaller structures. So, and I will include mostly the gravitational interaction, which is suddenly very effective. Which is suddenly very effective in this region of masses. How to describe this dark matter? Actually, the method to describe is, since the occupation numbers are large, then we can just solve the classical field equation. Moreover, since the dark matter is non-relativistic, its energy, the energy of each particle, is of approximately its mass. So this means actually that the field of this axion dark matter or axion-like particle, it oscillates like e to the minus EMT or e to the plus EMT. Anyway, the main frequency of this wave function is mass. And if we multiply this fast dependence on time by slow dependence on time in x, psi of tx, this will constitute the non-relativistic ansatz. And plugging it into the equation, we'll get the non-relativistic equation, which is just like the Schrödinger equation for the field psi, for the non-relativistic field psi. And here I introduced the gravitational potential U, which of course should, in non-relativistic approximation, it should satisfy the Poisson equation. So these two equations are just the Schrödinger Poisson system of equations, and they describe the non-relativistic and particles self-interacting via gravitational interaction. And if I don't write psi to the cube term in the right-hand side, and I won't for the most part of my talk, In this case, this will be just a gravitational interaction and nothing else. So what is important for me in these equations, and that there is a solution. There is a particular solution called Bose star or soliton or boson star. There are many names for one and the same object. And the object is as follows. The solution psi sits inside the potential well, its own gravitational potential well U, and it occupies the lowest level in this potential barrier. This means that psi equals to psi of r times oscillatory exponent, and U satisfies, well, consistently satisfies a Poisson equation, which is sourced by psi. So this is, one can say that this is a drop of Bose-Einstein condensate where each particle occupies one and the same level in the potential, its own gravitational potential, and it is self-bound. It's like a star. That's why it's called Bose star. So basically, Bose stars are characterized by their mass, one parameter, and it can be arbitrarily large if they do not interact at all. But if they do interact, well, actually, well, at some point, Bose stars can form black holes, but this is a very large mass. Yeah, so actually, if particles do interact, there is a mass cannot be larger than some limit if they interact attractively, because if self-interaction is included, the and mass is large, at some point it is the interaction, the attraction, it overcomes the pressure, and the Bose star starts to squeeze. Okay, uncontrollable, developing very high densities, and it develops a spiky profile, almost singular profile. So these are Bose stars, and we want to consider their formation actually inside the realized halos. So this is kind of the brute force simulation which we performed like in 2018. And it shows the realized halo, and you should imagine that we just cut a cube inside this halo, and this is the section of this cube. Let us consider the initial state of random waves. So we fix some momentum distribution of a field and give random phases to this field. And the Broglie wavelength is much smaller than the size of the system. So we are in the kinetic regime. We want to find out whether there are some Bose stars, some Bose condensate forms during evolution. So we switch on our computer and evolve it numerically. And this is the final state in the left bottom corner. It has an object, a very dense object, and spherical object inside. And this is precisely the Bose star. If you extract this object from the simulation and compare its profile with the profile of the Bose star, it's exactly the Bose star. So this calculation showed that actually the Bose stars are formed during numerical evolution. And actually, there are many evolutions and physical ones where the Bose stars form. Actually, there was a very notable simulation of Bose star formation in dwarf galaxies. So people were considering fuzzy dark matter forming dwarf galaxies, and there was a Bose star in the center of each and every one of them. And actually, more recently, there was a simulation of axions, QCD axions in very small structures, axion mini clusters, which have mass of order of 10 to the minus 13 or 14, solar masses, and they're small, and that's why QCD axions can condense and form Bose stars in their centers. Actually, so there are simulations and there are results. Why we're not satisfied with that? So we need theory. We need to make approximations, and we need to somehow to predict something without resorting to simulations on the supercomputers. And simulations are hard in kinetic regime when the Broglie wavelength is much smaller than the size of the system. There are several length scales inside the problem, and this is bad for simulating. So now I am going to tell you about the kinetic description of this condensation process, and it will work as a systematic expansion in this kinetic parameter MVR much larger than 1. So how to derive kinetic equation? So so first you introduce Wigner's distribution, which is just a 2-point function of psi at different points, but just a Fourier from this 2-point function. And the correlator here, the average here is computed with respect to the ensemble of random waves. Okay. Second, we need to write a chain of equations for the correlators. And to do that, let me introduce shorthand notations. Okay, so I will omit many things. They are there, but I will not write them. I will not write constants. So I omit constants. And I will not write operators. So I will not write a Laplacian. This might be misleading, but they will not be on this slide. And actually, u equals to Laplacian to the -1 of modulus psi squared. Okay, so the green function times the psi squared. Okay, and the integral. I will not write the integral. I will not write the Green's function. And what is left is like dt psi equals to psi plus g times psi cube. Okay, and these are the things that I'm taking trace of. Okay, so now it is possible to write a chain of equations for correlators in finite space. And if you differentiate, time differentiate the 2-point function, you get a 2-point function plus g times 4-point function. And if you take a derivative, time derivative of 4-point function, you'll get 4 and 6-point functions. Okay, but the next step is perturbative approximation in the very common sense. So you take, you recall that in the case of free field or Gaussian free ensemble of waves, this is the same thing. You just you can any correlator is just a product of 2-point functions. So 4-point function is just a combination of 2-point functions, and this is called a weak theory. And in interacting theory, you can write the 4-point function as a product of 2-point functions plus so-called connected part. And of course, this connected part is of order of g. So you can plug in this representation into the equations, and actually you can just omit the term of order of g squared in the equation for 4-point function. This is the term which is proportional to connected part of the 6-point function. And this leaves only 2 equations for 2-point function and 4-point function out of many of infinite chain of equations for correlators. Okay, so but the first, okay.
Can I ask you a question?
Yeah.
When you define the Wigner distribution, usually the Wigner distribution is defined given the wave function without even doing any ensemble average. Here, your Wigner function is defined by averaging over phases. Is that what you're saying?
Yeah. Yeah.
And by doing that, does that mean your Wigner distribution would be positive definite or not necessarily?
If you are in the kinetic regime, which is the momentum p times x much smaller than 1, then there is an observation that the Wigner distribution is positive definite after averaging. But if you are outside of this regime, for example, if you consider system of finite size, very quantum one, px of order 1, then it can be negative.
Okay.
That is why it is not exactly the distribution function. And that's why we use it only in the kinetic regime.
Yes. Okay.
Okay. So now I have already arrived to the equation for the two-point function, which is a kinetic equation. Two-point function is related via Fourier transform to Wigner distribution. So this is time derivative of a distribution of phase space distribution equals to something plus connected part of the four-point function. So all terms in this equation, I like the left-hand side of the kinetic equation, and four-point function connected part of the four-point function is called the collision integral. This is just the approximation. So actually, in this form, you might think that this equation is not complicated. It is horrible because I omitted operators. I omitted the integral. But you can do two formal things. First of all, you have your approximation that px much larger than 1. This is kinetic approximation, and you can plug it into this system and simplify it. And secondly, Landau showed that you can simplify the collision integral, this four-point connected part of the four-point function, by doing the following approximation. You assume that the main contribution to this integral comes from the collision of particles which are at intermediate distances between p to the -1, the Broglie wavelength, and radius of the system. And this region, this intermediate region, Landau argued, and you can check it actually during calculation. This intermediate region gives a larger, logarithmically larger contribution into the collision integral than the boundaries. Okay, and this gives you the local equation. And the left-hand side is just the kinetic equation, like any kinetic equation. Plus, you get some terms, and these terms are time reversal, and they are related to the fact that you are considering not point particles, but waves, okay, or quantum particles, whatever. And there are corrections, which I will not consider, but they're there. And there is a collision integral, which is connected part of the four-point function, and you can get a form of this collision integral, well, more or less the same as in the Landau-Lifshitz book. I will not present it here, but I'll write an estimate for the relaxation time. So you represent your collision integral as f divided by collision time, and you approximate it in the following way. Instead of integrating over momentum, you multiply on momentum. So you estimate all integrals. Instead of taking a derivative, you just divide by momentum or x, whatever. And performing this rough estimate, you get the following equation for the relaxation time. This is relaxation time. And I have several remarks for you. First of all, it is proportional to velocity to the 6. This means if velocity goes to 0, then relaxation is infinitely fast. This is true because this is gravitational interactions. We consider gravitational interactions, which is long-range force. And if particles move with small velocities, they can interact at large distances. Okay, so actually this is more or less standard expression, because you can write it as the Rutherford cross-section times concentrations of axions times velocity. And the only non-trivial, so to say, factor is F in the denominator. So, this is the factor representing Bose amplification, because if the particles are in occupied state, they interact stronger and stronger by a factor of the occupation number. Sigma F is the strength of effective cross-section. Okay. Finally, you can rewrite this equation for in the case of a bound structure. Okay, and in the case of bound structure, you will get you can use the fact that velocity is a virial velocity inside this structure. So you can express everything in terms of radius of the structure and velocity. And the gravitational relaxation time equals to radius divided by velocity, free fall time, times this huge factor, the kinetic factor, which is much larger than 1 cube. So usually in kinetic relaxation, the relaxation takes time much larger than the free fall time. And it is equal to the free fall time if the Broglie wavelength is of order of the size of the system. But unfortunately, in the physical example which I gave you, formation of solitons in the core of dwarf galaxies, or formation of Bose stars, axion Bose stars in the core of QCD axion mini clusters, this is almost the case. So RMV is almost equal to 1. So they condense very fast. Okay. So this is the numerical check of the okay. So first, this is let me show the evolution distribution in the simulation. This is the simulation that we performed by solving the Schrödinger-Poisson system, not a kinetic equation, Schrödinger-Poisson system directly. But after solving it, we calculated the distribution function over energies. This is not a distribution over momentum, but over energies omega. So the horizontal axis is energy, and the vertical axis is the number of axions with this energy within the box, within the simulation box. And this is the initial distribution, and it starts to evolve slowly with time, and you see fluctuations above this distribution. And you see that it goes towards omega equals to 0, and it develops a spike in there. And it approaches some smooth profile in the at positive omega. This is profile which is close to some thermal distribution with some intermediate temperature. Okay, so this is kind of attractor, but thermal distribution has an infinite singularity at omega equals to 0. But in truth, we cannot obtain this singularity, so the simulation should go around it somehow, and it prefers to create a Bose star, a gravitational bound, here it is, gravitational bound system of axions, which has almost delta function-like distribution, okay? Its energy of each axion inside their own potential well is negative. So, so it is. This is yes. This reflects the fact that the Bose star is gravitational bound. Okay, so okay, so now we can test the kinetic equation. So we solve the Landau equation numerically, kinetic equation, and this picture shows the distribution at approximately some in the middle of some kinetic evolution, and green line is our simulations of Schrödinger-Poisson system, and points, yes, they represent a solution of the kinetic equation, and there is some agreement everywhere except for the small omega, And at small omega, Landau equations develops a singularity, and in reality, Schrödinger-Poisson system doesn't develop a singularity, it creates a Bose star. So the time of evolution, it is correct to describe, to estimate the time of evolution simply from kinetic equation. And this is a comparison of time of evolution from kinetic equation, well, on the horizontal axis, and from direct simulations. And there is an agreement again. Okay, so I have to conclude from the part one, I think that we do understand the kinetic mechanism of Bose star formation pretty well. Unfortunately, this is not precisely the mechanism which works in the case of fuzzy dark matter in the dwarf galaxy or QCD axions in mini clusters, but they're kind of on the boundary of this mechanism, and we can just have some intuition from kinetic equation. Actually, we have predictions because if mass of axion is larger than, say, 10 to the minus 20 electron volts, then there should be no Bose star in the center of dwarf galaxies. And this is, of course, hasn't been checked by numerical simulations yet, but okay. So there remain some open questions like how does the Bose stars grow, or there are people consider other kinetic processes, but there are people in this workshop that know this better than me, so better to ask them. And I finished with the first part, and I hope that I convinced somebody that actually the Bose stars, they form. Lem, can I ask whether we record something or not? Because I don't see the button, the red.
You don't see the red? There is on the upper left corner. There is there's actually a red dot that says being recorded. Maybe you don't see it.
So if you see it, then yeah. Sure.
Maybe this is a good time to ask you some questions. Is that okay?
Okay.
I want to understand maybe a little bit better the technical aspect of this Bogolubov chain that you talked about at the beginning. There you have exactly. So you have this ensemble average, and I want to just make sure I understand the nature of the ensemble average. If I think of the psi, the wave function, as a superposition of momentum modes, is the ensemble average only averaging over the phase, or is actually more than that? It could be because in principle that's the phase that is random, but the amplitude of each momentum mode is also stochastic.
Look, here in the derivation, you do not need actually to assume what is this averaging about. Okay. You have to assume that you start from the Gaussian ensemble. That's it. That's it enough to derive the kinetic equation. Okay. But in simulations, if you ask concrete simulations, so the concrete way how we constructed the initial state, we performed the Fourier. We started with Fourier transform of wave function. We fixed the modulus. We did fix it without any fluctuations, and we have chosen the random phases. I believe that, yeah, if you would have a random spread of a momentum, it would not change much, but we didn't do these simulations.
I understand.
Okay, so the second part of my talk will be about the death of Bose stars, and actually this is a good point to recall that usually we do switch interaction of axions with photons, and usually we write for QCD axions this is just A times F dual, or if A is axion, your axion is scalar. or your dark matter particle is a scalar, you can write AFF. Anyway, you usually introduce a vertex like A to gammas. Okay, yeah, I will consider mostly in this part example of QCD axions because it's more relevant. And in QCD axions, the coupling constant to gammas is tiny. Okay, so it's equals to alpha divided by 2 pi FA, where FA is a fundamental scale of axions. But actually, it's tiny only in simple models, and in the, well, even in simple models, you can change parameters, and the actual bound, it should be smaller than FA to the -1, where FA is the fundamental scale of axions. In simple models, but there are so-called clockwork models where GA gamma gamma is much larger than FA to the -1. Okay, so I should say from the very beginning that for parametric resonance, I will need larger coupling to photons than in benchmark models. But well, simple models will be enough. So two orders of magnitude larger, or even 50 times larger will be enough for me to get a parametric resonance. So if there is such a vertex, then there are two processes which are of interest. Axion can spontaneously decay into 2 photons. And actually, if electromagnetic wave passes through the axion, it may stimulate decay of this axion with larger probability. And this opens a possibility of avalanche production of gammas. Suppose there is some system of axions like of finite size, of size R, and gamma passes through this system. Say this is a Bose star of any finite region filled with axions. And actually, it might trigger decay of one axion, and it decays into 2 photons, and one of these photons may trigger decay of another axion into 2 photons, one of which should cross the system again and trigger decay of some other axions. Actually, it is easier to understand that a necessary condition for the avalanche to begin to develop more and more photons inside the axion cloud is that the photon traversing this cloud should induce decay of at least one axion. Okay, if it does, then okay, so there is an avalanche, everything blows up. And this is a cool process, and we decided to study it. And actually, the equation, here's the equation for the electromagnetic field interacting with axions. Axion is A in green. And how can we simplify again this equation? Like in the previous transparencies, look, the photons are created by axions, and axions are non-relativistic. So energy of axions is approximately mass, and energy of 2 gammas is approximately mass over 2. Since they are massless, then the momentum is approximately mass over 2. So if we consider resonance developing along, say, one axis, say Z axis, then the Z momentum is mass over 2, in frequency is mass over 2, plus minus. Okay, so this suggests an ansatz, a canal ansatz, that there are fast oscillating exponents e to the mass over 2 times Z plus T, Z minus T, or Hermitian conjugate. And you can multiply them with slowly changing functions of time and X. Okay, and here C plus is left moving wave, C minus is right moving wave, and you can plug it into equation and obtain this equation, this system of equations. Okay. Okay, so it also has first derivative in time, first derivative in Z, and no derivatives in other coordinates, because this is an I-canal equation in the basis of plane waves. Actually, the last term in this equation is the interaction with psi. Psi is axion, non-relativistic axion field, and it takes C minus it creates C++. And this is exactly the physics which was on the previous slide. By solving these equations, you can, well, consider developing the resonance. But there is another approximation which is also valid, because photons are fast. Their characteristic time is a crossing time. They move with the speed of light. And axions are slow. They move with, at best, with velocity v. So you can consider the background as almost time independent. And in this case, Ci plus minus, they develop exponentially. They either grow exponentially, or they decay exponentially, or they oscillate. Doesn't matter. So the exponential rate mu is much larger than the time of background. Okay, so if you plug this into the equation, we will get a Schrödinger-like equation. This is like stationary Schrödinger equation for the modes, for the growing modes of photons. And boundary conditions for these equations. Okay. Boundary conditions from these equations is easily deduced from the picture. So waves do not come from infinity. C minus should be 0 in the left-hand side of the picture, and C plus should be 0 in the right-hand side of the picture. And you solve this equation along different axes with appropriate boundary condition. You find resonant modes which grow, which have positive mu. Positive real part of mu. And after that, you can combine all these modes into the electromagnetic field, and this will be the solution. That's it. This is the general scheme of my approach. Well, in what follows, I will apply it to different problems. The first one is the static coherent axions. Which is the case of the Bose star. So we have a Bose star, and in this case, the velocity is 0, and you can solve the entire set of boundary value problem analytically using quantum mechanical methods. To this end, you need to consider mu, which was much smaller than radius of the Bose star to the -1, but in physical situation, this approximation is valid. Main thing that enters the solution is d of z, which is the integral of the axion wave function along the line of sight. Okay, it determines the profile of the photonic modes, which is just hat-like. It is localized on the Bose star. I didn't plot it. Actually, the same d integrated over the whole line, it determines the mu equals to d minus pi over 2. So condition for resonance is that the modes grow with positive exponent, and this integral times, which involves the coupling constant, actually, I didn't tell you, integral of psi times the coupling constant. So it should be larger than pi over 2. So this solution is general for any background. I didn't use the concrete background of a Bose star, but I did use the condition that velocity of axions equals to 0, that the axionic field is real. That's what I used to derive this solution. I obtained the general. This is a general condition for the resonance. If you substitute into it a Bose star background, you will get the following result, very natural, that if mass of the Bose star is large enough, then the resonance develops. Actually, this critical mass for the resonance, it's inversely proportional to the coupling constant. And now recall that if the axions they attract, they have self-interaction, attractive self-interaction, like QCD axions, then the large mass stars actually do not exist. They collapse. They shrink and collapse. So if we add this condition to this one, we will get that the stars which do not collapse, that the resonance is possible only if the coupling constant is large enough. And this number, actually, for QCD axions, it is, well, 2 orders of magnitude larger than the benchmark values, KSVZ, DFSZ. These are 2 orders of magnitude small. Actually, the picture is like this. Here's mass, it's horizontal axis, and here's coupling, vertical axis. And in the shaded region, the resonance is possible. In the unshaded region, the stars that would develop resonance, they actually collapse. Actually, we can check our calculations, our analytic result by performing a direct simulation. So here in this transparency, I present a simulation of where we solved numerically relativistic equation, full set of relativistic equations for the axion field and for the photon field. And actually the only serious approximation that we have made, very daring approximation, is that the axion field at all times remains spherically symmetric. And we didn't assume spherical symmetry for the photon field. Okay, so this is like just was the numerical method to check our result. And here is the result of numerical simulation. This is time, and this is luminosity of photons. This is, roughly speaking, the energy flux of photons from the Bose star. We start with a stationary Bose star. We switch on interaction with photons, and photonic field immediately starts to grow. And it grows exponentially because this is a log-log scale, log-log graph, and its exponent of growth is coincides up to corrections, of course, but coincides with our analytic result. But then the back reaction starts, and the photons, they burn some part of axions. So the resonance condition is no longer applied because some part of axions vanishes from the Bose star. And this mu becomes negative. But after that, the photon field remains in the axion star. It exponentially decreases with exponent given by the same formula. Okay, so this is kind of quasi-stationary level inside or subcritical Bose star, which is no longer supports resonance. But photons live in there for a long time. Okay, so now it is not natural to consider collapsing stars, because we saw that the larger the density of the star, the better the star for the resonance. But the large mass Bose star collapse, and they develop huge densities in their center. So now it is the first place in my presentation where I switch on attractive self-interaction. And I assume large mass of the Bose star, and actually I will consider the collapse of this object. Well, actually, the collapse proceeds in a similar way, like previous studies shown. This means as follows, that the star shrinks, but it develops a universal profile chi star. At every moment of time, it has the same profile. But to get a profile at larger time, you just squeeze this profile and you make it higher, multiply it by a number. Okay, so you squeeze it by a number, you multiply it by a number, you obtain a profile in the next time. And this profile is kind of universal, it doesn't depend on parameters. Yeah, so this is a good chance to get a universal description of the resonance. So we plug in this psi, this self-similar psi, into the equations for the photonic field, and we find not one but two modes of the photonic field which grow. And they grow, and yeah, so we find these modes numerically. So we solve this boundary value problem numerically. because this collapsing star, it develops velocities. These modes, they exist if G gamma gamma is 0.15 divided by Fa. This is 2 times better than the Bose stars, the QCD Bose stars, but still 50 times worse than the benchmark values for axions. Yeah, so we can compare this. Huh?
Sorry to interrupt. Can I ask a question about the self-similar collapse?
Okay.
That universal profile, is it mostly due to gravity, or is mostly due to the self-interaction, or maybe both?
It is due to self-interaction.
Self-interaction.
Yeah, gravity is negligible in this case.
I see. Okay.
It switches on almost immediately at the start of the collapse.
Okay.
Okay. So yeah, so this picture shows nice agreement between our theory and the simulation, but it's better for me to show the simulation. So this is the simulation of a collapsing star. It has nothing to do with theory. This is a simulation performed numerically by solving relativistic equations for axions and photons. So this is the section of the photonic field. It shows the photonic field density. And on the left-hand side. And on the right-hand side, this is X and Y section of the axion field, which is bounded to be, we took it to be spherically symmetric. And the last graph, it shows how the total luminosity is a function of time. So this is how it will develop the resonance. So at first, the resonance, the photonic field grows exponentially, and you see it as appearance of the field, of the electromagnetic field. Then you see that there is a very long stage where the back reaction of photons on axions is not negligible. And this is the only example where this stage is long. It is the collapse of Bose star. Somehow collapse, it drives in many axions and feeds the resonance. Actually, you see that the photonic field, it's just like chaotic. So it has a lot of rays, and these rays are distributed chaotically. This is because the axion star itself, it is spherically symmetric, so all directions are the same. But it starts from the quantum fluctuations, so which are random. Okay, so and finally now you see explicitly the circles. Okay, so these are wavelengths. These circles are yeah. So the distance between the small circles is wavelengths. So yeah, to conclude, I presented the simple, I believe, boundary value problem which can be solved to describe photons interacting with non-relativistic axions. And there are many applications, and these here are applications which we considered in our paper, just these ones, not the other ones. Well, you can consider two stars, and in this case, it's twice easier to ignite the resonance because the resonance condition is easier to satisfy. The integral is twice larger, but there is an additional condition. That it's important that these stars can be separated. It's not necessary for resonance for the stars to be coalesce or something. But the velocity, relative velocity of the stars, should be small. Then you can coarse grain equation for photons and obtain a kinetic equation. And yeah, in this case, we will describe resonance in diffuse axions. Actually, also you can consider the following. You can consider some radio emitter emitting light shining through the axions. In this case, you will get larger photon flux, outgoing photon flux than ingoing. And in this case, the Bose stars can act as radio amplifiers. Actually, the Bose stars are much better radio amplifiers than diffuse axions. You can perform an estimate with our results and see it explicitly that if the number of the mass fraction of Bose stars is larger than 10 to the minus 4, they win. Okay, so thanks for attention, Lem. Thank you very much.
Thank you, Dima. This is very, very nice.
Okay.
I have a number of questions for you.
Okay.
Let's start with the first part of your talk, where
Okay.
You talk about soliton formation. I wonder whether your theory can be used to also address this phenomenon. I think it was first observed in simulations by Jens Niemeyer and his group, that the solitons not only form, but they seem to actually have oscillations. Is that something that you could address with your kinetic theory?
It's hard to say. See, the soliton in kinetic theory actually is one cell in the phase space. Okay.
Yes. Yes.
So this is like a delta function. And I wonder what, a good question. I don't know the answer actually. I wonder how one can describe oscillations of this axion. Is this some axions which are close by to it in the phase space? But I actually, yeah, good question. I don't know.
Right. The oscillations suggest. The oscillation suggests probably, if I use this picture that you used earlier, where I can think of the wave function as a superposition of different modes, there's for sure there's one mode that is like the ground state, soliton state, but is superimposed with other modes, and the presence of this other mode probably is what is responsible for the oscillation.
Yeah. So thanks. So you can represent this mode as a kind of delta function in kinetic equation. So you introduce several modes, and you introduce occupation numbers of these modes into the kinetic equation, and in this way you can describe formation of oscillating modes. Yeah, you're right.
That's right. That should be
correct.
There should be some kind of interaction that you can term that govern the interaction between this particular mode, which is the soliton, with the rest of the mode.
Yeah, but I should comment that to this end, you need to calculate an amplitude of interaction of these modes to the ensemble. Okay, and it's not easy to do, and I believe that nobody yet calculated it.
Right. Okay.
Analytically. So this amplitude should be plugged into the kinetic equation.
Right. Nice. I was also curious about in the second part of the talk where you talk about parametric resonance, which is a very nice effect. At the very end, you discuss what happens when you have two stars, which is of course very interesting from an astrophysics point of view when you have a merger of stars. And you point out that for resonance, you need the velocity to be less than 1/mr. Can you remind us where that condition comes from?
Okay. So in our approach, this condition is very easy to come from. Look, we are searching for resonant modes. And the resonant modes has a wave function, C plus and C minus. And these wave functions, they have width equal to the width of the Bose star, of course. So they have like bell-like shape, and they are concentrated on the Bose star. So the typical momentum, so momentum spread actually, is the 1/r, where r is the Bose star radius. Actually, you should compare the spread of momentum with the with the shift of the frequency due to velocity. So this is just the Doppler effect. Yeah. You sit on this Bose star, and another Bose star comes to you with velocity 2v. Okay, and its resonant photons, they are shifted in frequency by mv. Okay, by velocity times frequency mv. And this shift should be smaller than the spread in frequency, the spread of the resonance. This is the condition.
Very nice, very nice. And do your conclusions depend a lot on whether the axion photon coupling is that of a pseudoscalar versus a scalar? Does it matter very much?
Okay, so theoretically it doesn't matter at all. I don't see why it would matter. In numerical calculations, we used a pseudo-scalar coupling.
Right. I see. Very nice. And your last point on the same slide on radio amplification, that I assume what you have in mind is basically photon from basically elsewhere just going through the star and get amplified. That's what you have in mind.
Yeah, not just the photon, but the photon, so suppose you just have a radio source, and basically you expect a narrow peak at frequency equals to mass over 2.
Right.
So that's what I'm considering, the height of this peak in Bose stars versus diffuse axions. And Bose stars are actually better. This was some.
Nice. And would there be a similar phenomenon as in the diffuse case? We know in the diffuse case, if I have photons propagating through the diffuse axions, the polarization get rotated. That would be similar in a Bose star.
Well, we will work in different. So I think that the answer should be yes, because nothing is special about the Bose star, but we didn't consider polarization. So we worked in some polarization basis. So this is a good question for the future. So I cannot comment in detail about polarization. It should rotate.
Right. Okay. Great. Thank you so much, Dima. This is super nice.
Thank you for listening. So let us switch off this section.
I'm going to turn off the recording for now.
Mm-hmm.